Hello friends, welcome back to our MOOCs course on the fundamentals of nuclear power generation. Today we are going to start our second module on the very interesting topic of radioactivity and nuclear reactions. I hope the module 1 has gone down well and you have understood the basics of the topic of nuclear power generation. If you remember carefully, in the module 1 we discussed only a few fundamental terms and concepts associated with nuclear power or the so called atomic power. Actually, in this particular juncture, I should mention clearly that the term atomic power, while it is a very common terminology used in several different kind of resources that you will find, it is actually not a correct representation of whatever we are discussing here, because like we have seen in the last set of lectures or in the previous module, that this entire discussion of nuclear power generation is associated with the nucleus. The source of energy is actually associated with the mass defect, with the concept of mass defect. Whenever we have a nucleus, its actual mass is always found to be slightly less than the individual mass of its constituents, and that particular difference is termed mass defect, and that is generally visualized to have converted to energy and is able to bind all the nucleons together in a very small volume. That energy is called binding energy, and whenever a nucleus breaks into its constituents, that binding energy is released. So, this entire discussion on nuclear power generation is associated only with the nucleus, and it has nothing to do with the electrons that are orbiting around the nucleus. Therefore, it is not correct to call the same as atomic energy, and we shall be sticking to this term nuclear power generation and nuclear energy only. Now, in the previous module, it was mentioned that there are two common types of nuclear reactions, fission and fusion. Depending upon their mass number, any nucleus, any unstable nucleus wants to go through some kind of reaction which gets its binding energy per nucleon higher, close to the maximum level possible, and for which they always try to go towards a mass number around 60. Accordingly, those who are having a low mass number participate in fusion reaction, and those who are having higher mass number participate in fission reaction. But none of those, fission in particular, are spontaneous in nature. A nucleus can't participate in a fission reaction on its own, rather some kind of external agent or external influence is required. Now, the details of that mechanism we shall be discussing in a later chapter or later module, but for this moment let us focus on something that is more spontaneous, which is radioactivity. Radioactivity can be defined as a spontaneous disintegration or decay of an unstable nucleus, which is generally characterized by the emission of particles and or electromagnetic waves, and also accompanied by release of large quantity of energy. So, it is a spontaneous phenomena because of which one nucleus gets converted to another nucleus. The nucleus with which it starts, in this case this particular one, we call that parent nucleus, and the product nucleus is generally termed as the daughter nucleus. And this particular conversion of one nucleus to some other nucleus is always associated with the emission of some kind of particle and also large amount of energy, and of course, not only particles, it can be just electromagnetic waves also in several situations. But this a single step kind of reaction is generally not a very common one, because most often this daughter nucleus itself is radioactive in nature, and that can undergo some further disintegration to produce its own daughter. Accordingly, we may have the formation of a radioactive chain which starts from some very heavy nucleus and goes on through a series of different daughters, all of which are generally radioactive in nature, and the chain is able to finish or able to complete only when we have some kind of stable nucleus form, that is something which is not radioactive and therefore, is not able to go through any kind of disintegration. The radioactive isotopes are often called radioisotopes, and we shall be also using this particular terminology. So, a radioisotope can undergo spontaneous disintegration, which we are calling as radioactivity, and because of this spontaneous disintegration it produces some other kind of nucleus. That means, this phenomenon of radioactivity is associated with conversion of one nucleus to another one. If we go to the periodic table, something that we have used in the previous module also, generally it has been found that some of the isotopes of this group of elements like thallium, lead and bismuth some of the isotopes are radioactive, while some of their isotopes, particularly for lead and bismuth, most of their isotopes are stable, but some of them can be radioactive. But for elements after bismuth, that is elements having atomic number greater than 83, all their isotopes are radioactive in nature. That is starting from polonium having a atomic number of 84 towards whatever we can we have known so far, they are all radioactive in nature, they are all isotopes are radioactive in nature. That means, we are talking about elements like radon, elements like thorium, elements like uranium, plutonium, which are very common in case of nuclear power generation, and of course, radium, which I have not mentioned earlier. They are highly radioactive in nature, and therefore, they can't have any kind of stable isotopes. All their isotopes participate in some kind of radioactive decay or disintegration. But it is not that only from this atomic number of 81 onwards we shall be talking about radioactivity, rather several elements with very low atomic number can have radioisotopes or can have radioactive isotopes, like some of the isotopes of sodium or potassium can be radioactive in nature. Corresponding examples will be coming later on. And now, we have a new term, that is transmutation. Transmutation refers to the conversion of one nucleus to another, that is by the radioactive reaction. Whenever one parent nucleus gets converted to a daughter nucleus, that particular phenomenon we term as transmutation. Now, transmutation can be of different kinds. We know that any isotope is characterized by the number of protons and neutrons in it. So, whenever there is change in either in the number of protons or in the number of neutrons, or maybe both, that definitely is a transmutation. Therefore, the phenomena of nuclear transmutation can generate an isotope of the same element when there is change in only in the number of neutrons, or can generate altogether a different element when there is change in the number of protons as well. And here I would like to introduce a few more terms. Isotopes was of course discussed earlier, which is very important from nuclear reaction point of view, and isotope we know that refers to nucleus which are having the same atomic number, but different mass number because of the presence of different number of neutrons. We have got examples earlier. Here we have examples of two different cobalt nucleus, both are having 27 number of protons, but the number of neutrons are different, and accordingly one is having a mass number of 59, other is 60. So, they are isotopes of each other. But now we have three more terms. First one is isotone. It refers to those nucleus which are having different number of protons in them, but the same number of neutrons, and accordingly their atomic number and mass number both are different, but only the number of neutrons are the same. Like here we have the examples of nitrogen and oxygen, or one particular isotope of nitrogen and one particular isotope of oxygen. The natural nitrogen isotope has 7 proton and 7 neutron in it, giving a mass number of 14, whereas this particular isotope of oxygen is having as usual 8 protons, but it is having 7 neutrons and thereby a mass number of 15. So, both these two isotopes nitrogen and oxygen, they are having different mass number and different atomic number, but their number of neutrons are same and they are called isotones. Other is isobar. Isobar means the mass number is the same, but their number of neutrons and number of protons in the nucleus, they are both different, but because of their combination the mass number is same. Like here we have the examples of two isotopes. First one is phosphorus, which is having 15 number of protons and 17 number of neutrons, whereas the other is sulfur, which is having 16 number of protons and 16 number of neutrons. So, their mass number is same, both are 32, however, their atomic numbers are different. So, this is isobar. And finally, is isomar. Isomar basically refers to the isotope of the same element, two different isotopes. In fact, I should not call that two different isotopes, because they are having the same number of protons and neutrons. So, giving the identical values of atomic number and mass number, however, their energy states are different. Like here we have examples of two different xenon isotope, both are having mass number of 131 and atomic number of 54. However, this particular is having an M associated with it, which actually refers to an excited state, that is, it is having higher amount of energy content with it. And whenever this second isotope of xenon undergoes some kind of transmutation process, which is associated with the release of only energy, it can get converted to the other one. This topic of nuclear transmutation was first reported by Rutherford and Frederick Soddy in 1901, as they observed the conversion of thorium to radium during their experiments. It was completely a natural phenomenon which they observed. Before I come back to this, I should establish the relationship between transmutation and alchemy. Alchemy is a, you probably know, it is a dark side of science, something that has been practiced since as old as 9th or 10th century, where alchemists tried to have some kind of process by virtue of which they can convert some less precious metal or element to some more precious one. Very common example can be the attempt to convert lead to gold or mercury to gold. So, basically what they are trying to achieve, that is transmutation only, to convert the nucleus of lead or mercury to the nucleus of gold. This is some kind of periodic table that they used to use that time. Now, alchemy is a very much debated topic, and it is doubtful. While there are several alchemists claim to have some kind of success, it is doubtful whether there is any kind of truth into that. But the phenomenon of transmutation, when that was first identified by Frederick Soddy and Rutherford, that is definitely the first reported phenomenon of transmutation. Actually, there is a very funny story associated with this. It is said that when they first observed this particular phenomenon of conversion of one nucleus to another, Soddy screamed, "Oh, we have seen transmutation, or we have got transmutation." And it is reportedly said that Rutherford just tried to be very cautious and to asked him not to be so anxious or not to be so joyful, because they make it their head of thinking this is alchemy only. So, alchemy is something that is generally not permitted in the scope of science, and once this phenomenon of transmutation was achieved in 1901, several researches went after that, proving that the conversion is definitely possible. But just to differentiate it from alchemy, it has been proved that it is definitely possible to convert something like lead or mercury to gold. The process is generally associated with extremely high cost, which is definitely much more than the actual price of gold, and so there that is not something that is suggested from industrial point of view. But the objective of alchemist was completely different. Now, the discovery of the phenomenon of radioactivity probably started when the X-rays were invented by Röntgen around 1895, and then came the experiments of Becquerel. Becquerel that time was working with the phenomenon of fluorescence, and after hearing the discovery of X-rays, he thought about checking or finding the relationship between fluorescence and X-rays, and therefore, he took his sample, which is believed to be uranium sulphate, and put it into the sunlight, and also took a few photographic cells, covered that with black paper, and placed that close to his samples. So, if there is any kind of radiation emitted from the samples, that will be detected by the photographic plates, there will be impression printed on the plates, and so that will establish the establish the presence of any kind of emissions. But unfortunately for him, that time the skyline of Paris was cloudy for several days. He was unable to do the experiment, and there finally he had to abort the idea, and he put his photographic plates and also his sample into a drawer. As there is no scope for doing any further experiment because of the lack of proper sunshine, those samples remained inside the drawer for several days. But probably just out of whim, a few days later, Becquerel decided to develop his photographic plates, and to his surprise, he got something like this. This is believed to be the picture of this photographic plate which Becquerel developed. Clearly, there was impression. Now, this can't be X-rays. This impression proves that the sample has definitely emitted something, and that has been captured by the photographic plates. In fact, here you can see a cross kind of structure. There was actually a cross that was kept on top of that photographic plates, or those photographic plates, and clearly an impression of that one is also visible. But this one can't be X-rays, because there is no source of power, and X-rays require some kind of energy source, electricity or sunlight or something, as per the belief that time. and therefore, what Becquerel identified definitely is something that is different from X-rays. So, he termed that as U rays. The whatever Becquerel discovered that time, he called that U rays, just to differentiate it from the X-rays. But he was not able to characterize this for later on, or that time he was unable to characterize this any further, and what the contribution from Becquerel probably was limited only to this. From that point, it was taken forward by the Curie family. Basically, Marie Curie started her PhD more or less at the same time around 1896 and decided to work on this U rays. Soon after, along with her husband Pierre Curie, she identified several things. Firstly, they identified that thorium is also radioactive similar to uranium, and then they identified another element which was found to be at least 1,000,000 times more reactive than uranium, and in memory of their birthland Poland, they named that polonium. And then they identified radium, also the name was given by themselves only, and radium was found to be 2.5 million times more reactive than uranium. The term radioactivity was also coined by them. So, in acknowledgement of their discovery and their seminal work on this field of radioactive emissions, Marie and Pierre Curie and also Becquerel received the Nobel Prize in Physics in 1903. Marie Curie was the first woman to receive the Nobel Prize. Later on, around 1910, Marie Curie alone that time, following the death of Pierre Curie around 1906, she was successful in isolating the metallic radium and also defined an international standard for measuring the radioactive emissions. Now, again in acknowledgement to her work in isolating the metallic radium, she received the Nobel Prize in chemistry, I think in 1913, and she remains to be only one of the 2 persons who have received Nobel Prize in 2 different disciplines. There are several works followed by different groups of researchers on the radioactive emissions, but that time radioactivity was something purely natural, that is people just were able to observe the radioactivity or emission coming out of different elements, but was not able to control that radiation. Only in 1934, Irene, the daughter of Pierre and Marie Curie, she along with her husband Frederick Juliet Curie discovered the phenomenon of artificial radioactivity. It is actually believed that Irene and Frederick Juliet Curie discovered the nucleon or subnucleonic particle neutron before James Chadwick in 1932, but they were not able to characterize that properly, and Chadwick received the Nobel Prize. But Irene and Frederick Juliet Curie jointly received the Nobel soon after the discovery of artificial radioactivity, because this is the discovery which showed that it is possible to control the radioactivity, and therefore, it is possible to control the phenomenon of transmutation. That means, if we can provide proper conditions, we can convert one nucleus to something else as per our wish almost. That is definitely something path breaking, which led to this led to several kinds of discoveries in future. Now, we are talking about emission from the particles, commonly or emission from the parent nucleus. Commonly, there are 3 kinds of emission that we are generally accustomed with: alpha, beta and gamma emissions, often called the ABC of radioactivity. Alpha particles are nothing but helium nucleus. Therefore, they are heavy in nature. They comprises of 2 protons and 2 nucleons, 2 protons and 2 neutrons, giving a total of 4 nucleons, and as per the terminology that we are following, they are commonly represented by 2 He4 or 2 alpha 4 or just alpha. So, whenever a particle, a parent nucleus I should say, undergoes some kind of alpha emission or alpha decay as is often called, there are 4 nucleons that is going out of its nucleus. Total number of protons and total number of neutrons present in the parent nucleus will be reducing by 2 each, and therefore, the daughter nucleus will be having 2 protons less and 2 neutrons less. Accordingly, we can say if the parent nucleus is having an atomic number of Z and mass number of A, the daughter nucleus will be having an atomic number of Z minus 2 and a mass number of A minus 4, because 4 number of nucleons, 2 protons and 2 neutrons has gone out of this, plus of course, the helium particle or the alpha particle that will come out of this. This is a common example, but I shall be coming back to these examples later on. Here we have a nucleus having 241 mass number gets converted to a Neptunian isotope having 237 mass number. The second is the beta particle. Beta particles are much lighter elements, they are basically electrons. Electrons we already know from the atomic structure, beta particles are the same and they are commonly represented just by the symbol of electron, whether it is -1 E 0 or -1 beta 0 or just beta. In this context, I would like to mention a few things like proton, neutrons and electrons. They are often represented during nuclear reactions the same way we represent isotopes. That is, say for proton, if we use P for proton, then we know that a proton is having a mass of 1, or a proton basically comprises of just one proton itself. So, it is having a mass of 1 and also 1 unit positive charge. Accordingly, it is said that it is having one atomic number sort of thing is 1 and its mass number sort of thing is also 1. Here this particular one is associated with the charge and this particular one is associated with the mass. If we follow the same convention for neutron, now we know that a neutron is also having a mass of about 1 AMU, but it is neutral. So, neutron is represented by a 0 in here and a mass and 1 here. And for an electron, if we see, electron is having one element of negative charge or 1 unit of negative charge. So, -1 comes here, but its mass is extremely small compared to the mass of proton and neutron. So, we shall be using a 0 here, just what is shown here itself. And this is the convention, therefore, we are using or we shall be using for rest of this particular course to represent proton, neutrons and electrons, and if required some similar elements. So, whenever a particle undergoes a beta decay, that is a beta particle is emitted from the nucleus, of course, there will be -1 amount of charge is going out of this, and accordingly if the initial nucleus is having Z as the atomic number, the daughter actually will be having 1 proton more. You can visualize this particular emission as a conversion of neutrons to proton and electron. If you see in the parent, the total number of neutrons n is equal to A minus Z, and in the second one for the, if this says parent, and for the daughter it is the A remains the same, but the number of proton has increased by 1. So, it is very clear if we compare between the two, that the daughter is actually having 1 neutron less than the parent, and this can be visualized as 1 neutron as per our convention, which we are representing as 0 n 1 gets converted to 1 proton and 1 electron. As per our convention, proton is having +1 charge, electron is having -1 charge, electron mass is 0 and proton mass is 1. So, both the atomic number and mass number remains balanced, and accordingly a beta emission or beta particle decay can be visualized as the conversion of 1 neutron to a proton and electron. The proton is used to increase the mass number, increase the atomic number of the daughter by an unit, whereas the electron goes out in the form of the beta particle. However, the mass number of the daughter remains unchanged, because while the number of neutron has reduced by 1, the number of proton has increased by 1. This is one typical example where the tritium, that is the third isotope hydrogen, is undergoing a beta particle decay and getting converted to a helium. Both are having mass number of 3, but while in tritium we are having 1 proton and 2 neutrons, in case of a helium we are having 1 neutron and 2 proton. And the third one is gamma rays. Gamma rays are actually not particles, they are just electromagnetic waves or photons, a very high energy photon. So, whenever a radioactive reaction is associated with a gamma emission, it is basically produces the same isotope, or I should say the atomic number and mass number of the daughter remains identical to that of the parent. However, its energy level will be lesser. compared to the previous case. It is an example of isomer, or we can say that the daughter is an isomer of the parent, because it is having the same number of protons and neutrons, but its energy level is lesser. Gamma rays being electromagnetic waves, this is one example here. Gamma rays being electromagnetic waves, they are highly penetrating in nature, whereas the alpha particles being the heaviest, they have very weak penetrating power. Actually, they can be stopped just by a very thin piece of paper. Beta rays are having penetrating power in between the alpha and gamma rays. There are 2-3 other kinds of nuclear reactions possible, but we shall be coming back to these reactions plus the other ones which may be possible in the next lecture. Here, let us just focus on this topic of radioactivity only. So, now we know that a radioisotope can undergo some kind of disintegration or decay to produce a daughter. Depending upon the nature of emission, alpha, beta or gamma or something else, the daughter and parents number of nucleons and protons can be related, but this kind of reaction has to be following some kind of laws, or rather that is the question whether the kind of radioactive decay follows any kind of principles or not. Here we can't have any kind of mathematical proof for this, because whatever we are going to say, that is purely phenomenological in nature, analogous to all the principles of thermodynamics and several principles of heat transfer and fluid mechanics. That means, this particular decay law or the law of disintegration is purely from observations or experiments. It has been found that there are 2 points. Number 1, the probability of disintegration is the same for all the nucleus. That means, say we have a sample of 100 nucleus. Now, each of the nucleus present in the sample are equally probable to undergo a decay in the next instant. That means, that the next decay can be of particle number 1 or can be of particle number 59 or can be correspond to the particle number 93. We can't say for sure. Similarly, if we focus on any particular nucleus, say we focus on particle number 50, it can undergo a decay in the next instant or may undergo after 5 minutes or may undergo after 30 years. It is not possible to say. This is purely a probabilistic phenomena. But the second point is that this particular probability or their probability of disintegration has been found to be proportional to the number of nucleus that is present in the sample at that particular instant. That means, if we put in mathematical term, if n is the number of nucleus in a sample, then its rate of disintegration, that is d n dt, will be proportional to the number of nucleus itself. And introducing a constant of proportionality lambda, which is called the decay constant, d n dt is equal to minus lambda into n. Here the minus sign indicates that the number of nucleus, basically n, reduces with increase in time. So, it is a very straightforward relationship if we have idea about this decay constant lambda. This is a first order ordinary differential equation from mathematics point of view, and to solve this we need to have one initial condition. Let us assume the initial number of nuclei is equal to n naught or n 0 at time t equal to 0. Therefore, if we integrate this equation from some time t equal to 0 to some general time t, then we have this. At time t equal to 0, number of nucleus is n naught and n t represents any general number of nucleus at in general time t, and after performing this integration, this is what we have. N t is equal to n naught into e to the power minus lambda t, that is, it follows an exponential form. Or if we see on graphs, it is just a representative graph. If we start with 100 number of nucleus at some instant t, then with time it reduces exponentially depending upon the value of lambda. Of course, the slope of the curve will depend upon the value of lambda. If lambda increases, that is decay constant is higher, that means there are more number of nucleus that is getting decayed within a given interval, or we can say the rate of disintegration is very high, and accordingly while for a low value of lambda we get a quite smooth curve like by this red line here. When the lambda is quite high, we get this green line which represents a very sharp rate of reduction. But it is a simple straight exponential relationship that is being followed by these radioisotopes. Such an exponential rate of decay also implies that it is not possible for the number of nucleus to approach 0, or it can approach 0 only at infinite time. Of course, the rate of disintegration keeps on reducing with time as the number of nuclei present in the sample keeps on reducing, but it will never theoretically reach a 0. Therefore, in this context we have the concept of half-life that is coming to picture. Half-life is defined as the amount of time required to reduce the number of radioisotopes present in a sample exactly to the half of its initial value. That means, if initial number of radioisotopes in a sample is n naught, then the time it requires to have exactly n naught by 2 number of isotopes in the sample is called the half-life. If we put this into the previous example or previous mathematical expression, rather putting n equal to n naught by 2, we get T h is equal to log 2 by lambda or approximately 0.6931 by lambda, a very important relationship from radioactivity point of view. We can clearly see the half-life and the decay constant are inversely proportional, and that their product is equal to log T. Also, putting this idea of T h into the previous expression, we can also represent n t by n naught as half to the power t upon T h. Now, if you represent this on a graphical platform, say at time t equal to 0, we are starting with n equal to n naught. So, if we follow the time after an T h amount of period is elapsed, that is an amount of time exactly equal to the half-life, then the number of elements present in the sample also will become exactly half, that is n naught by 2. If we go another T h amount, that is from T h to 2 T h, then it will become half of this n naught by 2, that is n naught by 4. If we go another T h amount, that is from 2 T h to 3 T h, it will become half of this n naught by 4, that is n naught by 8. And this way the curve becomes more moderate as we move on in time, and the total number of nucleus keeps on reducing exponentially, but it will be requiring infinite amount of time for this number of particles to reach an absolute 0. Here this equality should not be there, actually it is just n naught into half to the power t by T h, as we have already seen in this expression, the previous expression. Now, the concept of half-life is an extremely important one from radioactivity point of view, because half-life for a radioisotope is similar to our fingerprints. Each radioisotope has its own half-life, and therefore, the knowledge of half-life for an isotope is sufficient to identify this one. I repeat, every radioisotope has an unique value of half-life, and it is not possible for two radioisotopes to have the same value of half-life. Therefore, half-life measurement is one popular way of identifying radioisotopes. Yes. If we see this particular list, here we have several elements listed and along with their half-life values, and also the principal kind of reactions that they generally suffer. Like if you see that tritium is having a half-life of 12.33 years, that is if we are having a sample of tritium containing 500 number of isotopes to start with, only after 12.33 years the number will become 250, and for reducing 250 to 125 it will require another 12.33 years. But of course, the range of half-life is quite large, as you can see, whereas we start with a value of 614 second, some of the isotopes can have extremely large value of half-life, like you can see for uranium 238 is of the order of 10 to the power 9. I think thorium is missing from this chart. Thorium can also have an half-life value even higher of the order of 10 to the power 10 years. Here this Y refers to years, whereas S refers to second and H refers to hours. So, some isotopes can have very small half-life, like here you can see nitrogen 16 has a half-life of only 7.313 seconds. That is, only within a period of 7 seconds the number of nitrogen isotopes will become half of its initial value, but some of them can definitely be much larger. And the last column in this table shows the principal kind of decay that they suffer, like nitrogen is generally associated with the decay of nitrogen 16 associated with the emission of beta and also gamma rays, whereas for uranium 238 it is generally associated with alpha decay, which releases 4.040 amount of electron volt amount of energy. Now, the top of the chart we have neutron. This is a very interesting one. As I have mentioned earlier, a radioactive decay of neutron is associated with the production of one proton and one electron, and as we can see from the chart, a free neutron is able to undergo a decay with a half life of 614 second, thereby producing 1 proton and 1 electron. Most of the natural radioisotopes are heavy in nature, but as I have mentioned, there are exceptions and several of them are listed in this table. Very common examples can be tritium or carbon 14 or potassium 40, which all of them are produced during natural nuclear reactions and generally are available in plants and animals. Like potassium 40 is quite common in several kinds of plants. Natural potassium contains is about 0.0117%. Yes. Whereas tritium is also present in a very trace quantity in normal water. But most of the isotopes that we need for energy productions are the heavier one in nature, and thankfully all of them are having quite high half life. Like uranium is having half life of uranium 238 is having half life of 10 to the power 8 years, whereas uranium 235 and uranium 238 is having even higher of the order of 10 to the 9 years. That is a very good information to have, or I should say, thanks to their very large half life, they are still existing in this nature, existing in this universe. Had their half life been very weak, they would have vanished long back or within a much shorter period of time. Only because of their long half life, they are able to survive on this universe. So, we move on to define another term, that is called activity. Activity is nothing but this rate of decay or disintegration, and it is equal to minus dn dt or equal to lambda n, where lambda is the decay coefficient. So, initial activity corresponds to the value of the activity at the beginning of the selected time interval t equal to 0. Accordingly, we can write initial activity A naught is equal to activity A at t equal to 0, that is minus dn dt at t equal to 0, that is equal to lambda into n naught, where n naught as per our previous notation is the initial number of nuclei present in an isotope. So, putting this expression for A and A naught in our original expression, we get A t equal to A naught into e to the power minus lambda t, that is the change in activity with time can also be related to the decay constant lambda. This is again another exponential curve, and if we plot it graphically, it will represent a similar kind of nature as we have seen for the decay law. Occasionally, there is another term that is used to characterize nuclear fuels, that is the mean life, or given by the symbol tau. It is the average time elapsed before the decay of an individual nucleus. It can be viewed as the average lifetime of a single radioisotope since its birth. Mathematically, it is found to be proportional, or rather inversely proportional to this decay constant, and so we can also write it as the half life divided by log 2. So, all these information, that is half life, activity, mean time, they all are associated with a radioactive fuel, and these are important informations to know whenever we are trying to choose some kind of radioactive fuel in any kind of application that we are looking for. There are a few examples of the mean life, like we have seen for a free neutron, it can undergo a very prompt decay because its half life is extremely small. Accordingly, its mean life is coming to be only 885.8 seconds, whereas uranium 235 has a mean life of the order of 10 to the power 9 years. That means, if we have one uranium 235 nucleus, it is very likely to survive on an average a period of 10 to the power 9 years, and so it is quite easy to store this fuel and use them for whatever purpose that we would like to have. This term activity is measured with the unit of Curie. I have mentioned earlier that Marie Curie proposed one international scale for measuring the activity of the radioactive isotopes, and that is equal to the activity of 1 gram of radium 226, and in her memory that is called the Curie, which is actually 3.7 into 10 to the 10 disintegrations per second, that is within 1 second. If the 3.7 into 10 to the 10 number of isotopes are suffering disintegrations, then we call this particle to have activity of 1 Curie. But this is generally a very large number to have, as we are talking about disintegrations per second of the order of 10 to the power 10. So, quite often the other unit Becquerel symbol BQ is often used. This is actually the SI unit of radioactivity. Of course, I should not I do not need to mention about the source from where this name came, but this SI unit of Becquerel can also be related to the Curie, as 1 Becquerel is equal to 2.703 into 10 to the minus 11 Curie. Becquerel again is a very small unit, So, quite often we have representations in terms of kilobecquerel or megabecquerel, that means multiplied by 10 to the power 3 or 10 to the power 6 or similar. Yes. Also, to measure the biological effect of radiation in human tissues, there are units like Rontgen and Gray which are often used, but we shall be discussing more about them in a later module when we shall be talking about the biological effects of radiation. The measurement of half-life is a very important one, because just by measuring half-life we can easily identify the radioisotope itself. We do not need to know the number of protons and neutrons separately. There are several ways. This is one of the classical ways of doing this, that is by the Geiger-Müller counter. This counter is actually a cylindrical chamber which is having an wire stretched along its longitudinal axis. So, the chamber wall is charged to become the cathode, whereas a positive voltage is applied on the wire, making it the anode. The cylinder is filled with a low pressure inert gas like helium, neon or argon. Quite often you will find a mixture of argon and ethyl alcohol has been put into the cylinder. Whenever there is some kind of ionization particle or photon that is passing through the gas, it becomes conductive due to the ionization for a very brief period. This ionization is sensed by the electronics of the device, it is amplified to a much larger amount, and therefore, it produces a very detectable pulse. The pulse is measured by this particular counter, which just counts the number of pulses that is observed during any experiment. Now, this pulse is counted to provide a measure of the activity of this particle, and once we know the activity or we can always calculate the decay constant and the half-life of that. Geiger-Müller counter being a very classical element, it is generally robust in structure and also relatively very cheap, but it has a few disadvantages, like it is unable to differentiate between different kinds of radiation, as the final output pulse that we get, that is independent of the energy of the incident radiation. So, we shall not be able to say exactly at what energy level the radiation is able to reach the counter. And secondly, inability to measure high radiation rate owing to dead time. Now, once the tube undergoes one set of actuation, it requires some time to recover, and that time is referred to as the dead state. So, when the radiation rate is very high, it will not be of any value. But there are several other kinds of counters, gas field counters and a few other kinds of counters are also available in modern days, which are used for measurement of radioactivity or the half-life in general. We would like to discuss about them in later chapter. Now, we come to the radioactive chains. As I have mentioned, whenever we are having one radioactive element undergoing a decay, on radioactive isotope undergoing a decay, it produces a daughter. The daughter is very commonly is radioactive in itself, and accordingly the daughter nucleus can also undergo some kind of reactions. But before we go to such kind of chains, let us just stick to a binary reaction. Here we have a single step reaction where A is the parent nucleus and it undergoes a radioactive decay following a decay constant of lambda and produces an isotope B. Now, for any particular species, the conservation equation can be written as the time rate of change is equal to the rate of generation minus the rate of decay. It is a very straightforward balance equation. So, for the species A, we can write that its time rate of change, that is dN dt, is equal to, there is no source for A. So, the rate of generation is 0 and the rate of decay as per the principle that we have studied earlier, that is proportional to the number of nucleus for A itself, and so can be given as lambda into N A. Similarly, for the species B, dNB dt is equal to, it has a source from A, that is whatever is the reduction in the number of molecules for A following this decay rate, the same will be the gain in the number of isotopes of B, and so dNB dt is equal to lambda N A minus 0, as B is not undergoing any further disintegration. And also at any time instant we can say that the time rate of change of the total number of isotopes present in the sample has to be equal to 0. This can be understood from common sense, because an isotope of B can be formed only because of the degradation or decay of the isotope A, or whenever there is decay of one isotope of A, we get precisely one isotope of B only. Therefore, total number of isotopes remains constant inside the sample. that we are talking about. Now, we have two ordinary differential equations. This is our equation number 1 and this is our equation number 2, and we need to solve them using two initial conditions. Here our condition is n equal to n a naught and n b equal to n b naught at time t equal to 0. Putting that and also taking into consideration the condition of d dt of n a plus n b equal to 0, we get these as the final solution, where n a follows the exponential relationship as usual, whereas n b is also having a modified kind of exponential form, and this can be a graphical representation of whatever we are talking about earlier. Here n a is reducing sharply, this is given by this red line, and correspondingly n b is increasing at the same rate. Here total number of nucleus has been non-dimensionalized by the initial number of nucleus, so that it is scaled to a value, final value of 1, where 1 is the initial number of nucleus A is having. This particular case uses n a not equal to 1 and n b not equal to 0 and take a lambda value of 1. Accordingly, initially the value of A isotope is equal to 1, value of B isotope is equal to 0, and their summation remains balanced, that is remains equal to 1 throughout the duration that we are having. You can also see in this period it seems that the number of A isotopes is equal to 0 and same for B is equal to 1. Actually, there is a very tiny gap that remains, and A can become 0 only after an infinite period of time. Now, this is only a single step reaction, but in practical cases radioactive reactions happens in chains. Each reaction is followed by another one and then another one, as often the daughter nucleuses are also radioactive in nature, and this kind of chain continues till the appearance of some non radioactive kind of element. Like here we have the example of an uranium-238 decay chain. If you follow, here we are starting from this particular point U-238, it follows an alpha decay. So, alpha decay means we have seen in alpha decay means the atomic number will be reduced by 2 and the mass number will be reduced by 4. Following that, we get this particular thorium isotope which undergoes a beta decay. Now, beta decay means we have already seen that the mass number will remain the same, but atomic number will increase by 1. So, uranium is having an atomic number of 92, whereas thorium is having an atomic number of 90, and this palladium this protactinium is something in between, that is having an atomic number of 1, and this chain continues with subsequent alpha and beta decays till we reach this particular state of lead 206, which is a non radioactive one. So, no further disintegration allowed. Actually, you can find that during this chain, where is starting from uranium-238, actually uranium-234 comes back somewhere in between, whereas while we are ending up with lead-206, there are other elements like lead-210, which is also, and also lead-214, which are radioactive in nature. So, they undergo some kind of decay finally to end up with lead-206. Similarly, we have the chain for thorium here, thorium-232. Again we are starting with thorium-232 and it undergoes an alpha decay. So, the product is having a mass number of 4 less than thorium and atomic number of 2 less than thorium, where we find it as a radium, and that keeps on undergoing subsequent alpha and beta decays finally to end up to the lead. One interesting thing here to note that after reaching this bismuth 212, there are two kinds of reactions possible. One where the bismuth undergoes a beta decay to produce polonium, and then which goes to alpha decay through an alpha decay to lead to lead. The other possibility is that the bismuth undergoes an alpha decay producing thallium here, and this thallium undergoes a beta decay to produce the lead. So, it is possible to have different kinds of radioactive reactions, and this kind of chain formation is very common in any kind of radioactivity. In fact, all the heavier nucleus that we can associate it with radioactivity, they undergo such kind of chain, and most often than not you will find that lead is the last element where everything is finishing on. So, in the next lecture we shall be starting with the analysis of one such chain. We have seen the analysis of a binary radiation reaction in the previous slide, where we are having just 2 isotopes involved. Now, in the next lecture we shall be taking 3 isotopes together, which can be visualized as some in between step of these radiation chains, and analyzing that for to identify the mathematical expressions with which we can represent their rate of decay. So, thanks for your attention. Hopefully, in the next class you will be coming with a better idea about this radioactivity, so that we can proceed further to understand different kinds of possible nuclear reactions. Thank you. Thanks a lot.